So, we are going to continue for the next couple of chapters on the theme of carbonyl chemistry, but we're going to change our nucleophile. Our nucleophile in chapters 13 through 16, right, usually was something small and negatively charged. We were adding hydroxide or an alkoxide or perhaps an amino group or an organolithium or Grignard reagent or cuprate to an aldehyde, ketone, or carboxylic acid derivative. But nature's got more nucleophiles than that, and so we're going to now talk about, for the next couple of chapters, the alpha carbon nucleophiles. And what do I mean by this? Well, let's go back to carbonyls. Let me make sure we're getting audio good. Here is a ketone, and just a little bit of stuff we will use to talk about ketones. This is the carbonyl carbon. This carbon is adjacent to the carbonyl carbon, so we will call it the alpha carbon for adjacent, but in Greek letters, I don't know. So, the alpha carbon. Now, you may have learned or remember from 351 that the pKa of a typical sp3 hybridized carbon-hydrogen bond on a hydrocarbon was around 50, which is nuts. That just means that never in a gazillion years of the history of the universe did water ever remove a proton from a hydrocarbon like that, okay? However, if you come over here and look at this related compound, we still have an sp3 carbon-hydrogen bond, but the pKa of this proton is 20. So that's 30 orders of magnitude, 10 to the 30 times more acidic. And this is getting in the range of things that are maybe accessible to bases like hydroxide. Let me draw for you the conjugate base of these two molecules, and that will help explain why that proton alpha to the carbonyl is so much more acidic than just a regular sp3 hybridized carbon-hydrogen bond. All right, so here are the two carbanion conjugate bases. And the one on the left has resonance stabilization because of that neighboring carbonyl group. We can actually move these electrons to form a carbon-carbon pi bond and then move the electrons from the carbon-oxygen pi bond out onto the carbonyl oxygen. You've probably seen that before, but I don't know that we've ever used it in this sort of explicit way to talk about why alpha protons are so much more acidic than the regular carbon-hydrogen bonds. So you've got a resonance stabilized conjugate base. And not just any resonance stabilized conjugate base, but one in which the electrons can be both simultaneously on carbon and oxygen, which is electronegative. This conjugate base has a name. We call it an enolate because it is, the enolate is the conjugate base of the carbonyl compound. And it is also the conjugate base of a related isomer of the carbonyl compound, which is called the enol. Right? So if we had some strong base, we could remove the proton from the alpha carbon. That would put us in equilibrium with the enolate, and then depending on whether the enolate got protonated on the alpha carbon or on the carbonyl oxygen, you might make one of these two isomers, the ketone versus the enol. Okay? So that's why we call this intermediate an enolate. It's the conjugate base of an enol. Right, anything we want to ask about that? The enol and the ketone are isomers of each other. They are a special kind of isomer. They differ in the identity, they differ in the location of a pi bond and in the location of a proton. So those two forms, ketone form and enol form, we're going to call tautomers. And the process of going from one form to another is called tautomerization. So to do this, you would have a base remove the beta proton from, the alpha proton from your ketone. You generate the enolate. Resonance stabilization puts that negative charge on both the alpha carbon and the carbonyl oxygen. And then if you protonate on the oxygen, you get the enol. It turns out that if you compare the bonds formed versus bonds broken, the ketone has a bond between the alpha carbon and hydrogen, a sigma bond, and it has a pi bond between the carbonyl carbon and oxygen. The enol has a sigma bond between the oxygen and the hydrogen, and then a pi bond between the alpha carbon and the carbonyl carbon. And it turns out that the ketone form, those bonds are more stable than are the bonds in the enol. And you could look up numbers to tell you, you could confirm this simply by looking up numbers in a table at the back of your text. But in general, the ketone form is more stable. Oxygen carbon pi bonds are more stable than carbon carbon pi bonds because oxygen is more electronegative than carbon and holds electrons closer to itself, and closer to the nucleus is more stable. All right.
Does that mean that there's usually more ketone in a mixture of these?
Sure, yes. I mean, so how much of ketone versus enol, yes. So you're asking about the equilibrium between the two tautomers, ketone versus enol, and yeah, that's going to be, in general, favor the ketone form. All right? Another question you could ask is, what about the relative amount of ketone and enol versus enolate? And that percentage is really determined by how strong of a base you use. So I can talk about that in just a second, but...
So a tautomer is just, like, the definition is something that is almost the same, but not quite, or like differs in how? How is it different?
Tautomers are isomers that differ in, and only in, that's not, is that a thing? I don't know. That differ only in the location of a pi bond and a proton. So look at the things that are changing. Pi bond and carbon hydrogen bond, pi bond versus oxygen hydrogen bond. And the other thing about tautomers is that they can be interchangeable via proton transfer or just acid-base chemistry. Yeah. So one question you could ask about enolates is, how do you know how much enolate is going to be present? And the way you know that is you compare the pKa of the enolate to the base that you're using. So for example, let's take this ketone where the alpha carbon has a pKa of 20, and let's use hydroxide as a base. and we'll draw the conjugate base of our enolate. You can draw it in either of the two resonance structures is perfectly fine. And then on the other side of the equation, we have water as our acid here on the right-hand side, whose pKa is 16. So, in chapter 2 of 351, you learned that the strongest acid wins at losing its proton. So which side of this equation is favored at equilibrium? The left. And by how much? 4 orders of magnitude. So the equilibrium constant here, if we were to estimate it, would be 0.0001. Okay. So that means something like 99.99-ish, percent ketone and 0.01% enolate. That sounds like a small amount, and it is, until you realize that 1 mole of molecules is 10 to the 23. So if we had 1 mole of ketone, there's going to be maybe 10 to the 19 molecules of enolate versus 10 to the 23 molecules of ketone. And 10 to the 19 is still a fairly large number, and it's enough to do some chemistry with, particularly if that enolate can react in a way with something that leads to a more stable product. So we're still going to be able to do chemistry with enolates, even using bases like hydroxide. We'll call this sort of equilibrating enolate formation, because it's not your major, it's not 100% yielding. You only make a very little amount of enolate. Nevertheless, by Le Chatelier's principle, if we can shunt off the enolate into some other product, that will tend to pull more of the ketone starting material over in this direction. So we're going to be doing a ton of things in the next few chapters using enolates. You have a second option for enolate formation, and that is called, we're going to call that quantitative enolate formation. When organic chemists say quantitative, they mean 100% yield. And of course, everybody wants reactions that are quantitative. Let me give you same ketone starting material, but we're going to use a different base. Quantitative enolate formation simply means you use a base that is reactive enough that it can 100% remove protons, and you do that by comparing the proton that you want to remove, which has a pKa of 20, with the proton on the conjugate acid of the base you want to use. All right, so, and then we'll draw the enolate. This base is called lithium diisopropyl amide. It's basically an organic soluble version of NH2 minus. I tried to do a reaction in a lab here 20 years ago. I was taking Chem 455 and was trying to do a reaction using NH2 minus, sodium NH2 minus, and it didn't work, I think because the bottle of reagent was old, but also the sodium amide was not very soluble. Lithium diisopropyl amide, or more alphabet soup here for you, LDA for short, is organic soluble, and it is a very strong base, but it is a poor nucleophile because of sterics. And it's also somewhat expensive. So sometimes people ask, well, this is great. I can make 100% I can make my enolate using this base to 100%, and why wouldn't I always use LDA? And the answer is, if you can do the reaction cheaper and still get the product that you want, then you probably don't want to use the more expensive stuff. The reason this is 100% yield, though, is that the pKa of the conjugate acid of LDA is around 40. So that's an equilibrium constant that's more like 10 to the 20. And we're not going to bother with the 99 and the 18 other nines to give you a sense for how close to 100% yield this reaction is. We'll call this irreversible because the equilibrium constant is so large. So you can make the enolate either under reversible or irreversible conditions. There are situations where you would want to make it under equilibrating or reversible conditions, in part because of the expense. There's also an issue of regioselectivity that we have not yet talked about. And it will turn out that we will sometimes get a different enolate product from equilibrating enolate formation than we will from quantitative enolate formation. So it's important to have sort of those two different conditions in mind. All right. I want to say a little bit more about acidity of alpha protons. So far we've just dealt with ketones. I'll do that in a little bit. I want to continue on this theme of equilibrating enolate formation, though, for just a little bit versus quantitative, and show you another reason why it matters. But let's pause for any questions you might have. Okay? All right. So let's talk about regioselectivity of enolate formation. Notice that the ketone I chose is boring. It's symmetric. Your two alpha carbons are identical to each other, but there's no reason we had to choose it to be that way. So this matters for asymmetric ketones. So as an example, let's just add a carbon to our ketone. Now we've got two different alpha carbons. You have, we'll call it orange alpha carbon and purple alpha carbon. And therefore you have two different enolate possibilities. If you remove orange alpha proton, you're going to get the orange enolate that looks like this. We could also, if you want, draw its other resonance structure, which shows the negative charge on the alpha carbon. People prefer the resonance structure often where the negative charge is on the oxygen, because they're like, oxygen can better tolerate the negative charge. We'll have more to say about that in a little bit. We haven't talked yet about using enolates as nucleophiles. When we do, we will see that enolates act as nucleophiles almost always at the alpha carbon and not on the oxygen. There's a reason for that, and we'll talk about that. But here we have the orange enolate that we get by removing the orange alpha proton. versus the purple enolate that we get by removing the purple alpha proton. And then, of course, we could draw the other resonance structure with the negative charge on purple alpha carbon. So these are two different enolates, and they are regioisomers of each other. Now, it will turn out that enolate stability tracks with alkene stability, which you learned about in 351. So, which is more stable, orange or purple enolate? Purple, that is correct. This is more stable and therefore is more substituted. Sorry, let's back up. It is a more substituted alkene in the at least one resonance structure of the enolate, and therefore it is more stable. This is the less substituted enolate, and it is therefore less stable. Same reasons you learned in 351 apply. More substituted alkenes are more stable. That has to do with something called hyperconjugation, but we don't really need to go into that in a lot of detail now. But being able to recognize the difference between two enolates, the difference in how substituted they are, the difference in stability is pretty important. All right. So that's issue number one. Which enolate is more stable? When you have the possibility for two different enolates, which enolate is more stable? Stabler? Whatever. Okay. The second issue is, are you making the enolate under equilibrating or irreversible conditions? If you're making the enolate under equilibrating or reversible conditions, the most stable enolate dominates. Full stop. Okay? So let's go back here to our equilibrating enolate formation. I told you that given your choice of base and the fact that it's not basic enough to completely remove the proton from the enolate, your equilibrium constant is pretty small. That tells you that the enolate product for this equation is actually higher in energy than your starting materials. All right? So we can draw an energy diagram to illustrate that point. Here is our starting enolate. Here's the less substituted alpha proton. Here is the more substituted alpha proton. And we're using hydroxide as a base. And then we'll use, on the y-axis, sort of, we've got energy. And our starting material is in some energy well. And if we go this direction, we make the, let's see, keep everything. If we go to the left, let's say we remove the less substituted alpha proton and we make orange enolate. and water as the conjugate acid of our base. If we go this direction, we make the more substituted, more stable purple enolate and water as our conjugate acid. So still 99.99% of our stuff is unreacted starting material, but you've got an energy difference here between the less substituted enolate and the more substituted enolate. And that energy difference tells you that of the, what did we say? 0.01% of the 0.01% of enolate, most is going to be the more substituted purple enolate. Okay? And it doesn't matter which one of these two enolates forms faster. In fact, I without thinking chose how high to put these transition states. But it doesn't matter which one forms faster, because the reaction's under equilibrium. If it's faster to form this enolate, that's okay. It's just going to go back to the starting material. And on average over time, the molecules are going to traverse this energy landscape in all possible directions. And so this enolate is in equilibrium with this enolate, which is in equilibrium with this starting material. You're going to have a very small amount of enolate, but most of it's going to be here. Okay? Now let's say something about those transition states actually. I just sort of drew them arbitrarily, so we can go back and try to fill in some details. Which enolate do you think is going to be easier to, which alpha proton in the starting material do you think is going to be easier to remove? Orange or purple? Orange versus purple. Well, purple leads to a more stable enolate product, but if you say orange, why might that be? Sterics, yeah. You have a methyl group here versus an ethyl group here. This adjacent methyl group is going to get in the way a little bit of a base that wants to come and remove this alpha proton. So if sterics were the major issue, you would predict that at least kinetically it would be slower to remove the more substituted alpha proton than it is to remove the less substituted alpha proton. So let's edit our diagram to reflect that process. Let's put the transition state to get to this more stable enolate a little bit higher. I don't know what the numbers actually are, so this is probably exaggerated. But what we intend to show here is just that the pathway that leads to the more substituted enolate, the purple transition state, is higher in energy because of steric hindrance. Versus over here, the orange transition state is a little bit lower. And again, that is because a base has fewer things to contend with in trying to access the orange alpha proton. So for the transition state here in orange, we'll say just less steric hindrance. Okay. So we've got two different things at play. We've got stability. The purple enolate is more stable, but the pathway that leads to it is a little bit higher in energy. The orange enolate is less stable, but the pathway that leads to it is is lower in energy. Okay? So you got two energy differences to consider. Energy differences between these intermediate wells. This is an issue of thermodynamics, which enolate is more stable. This energy difference here is an issue of kinetics, which enolate forms fastest. Under reversible conditions, thermodynamics dominate. Kinetics don't matter. If, as soon as you make the enolate, you can go back over the hill and back down to starting material, it doesn't matter at all how fast that process happens. Okay? So under equilibrating conditions, you're going to get the most stable enolate. Sometimes people call the most stable enolate the thermodynamic enolate. That's a multi-syllable word that sometimes confuses people. If you want to use it for shorthand to remember this discussion, you certainly can. I generally don't. Because I can't spell it. Thermodynamic enolate. Okay. Questions so far? So let's just change the energy landscape now by saying let's do the reaction no longer under equilibrating conditions, but let's do the reaction under irreversible conditions. That is, let's use a base that's so strong that once we make the enolate, there's no going back. Under why can't I spell irreversible? All right, let's try again. Under irreversible conditions, the fastest to form enolate dominates. Okay. So how does changing the base, basically we're doing this by using a base that's so basic that as soon as the enolate forms, you're done. How's that going to change our energy landscape? You're going to leave the enolates in the same relative positions. So let's just edit this to begin with, get rid of all of this, a bigger eraser, get rid of the lines. And in fact, let's just use a purple line to indicate the position of the more substituted enolate, and an orange line to indicate the position of the less substituted enolate. Their relative stability isn't going to change, but now instead of using hydroxide versus water, we're using lithium diisopropyl amide, or LDA. And here's the conjugate acid of LDA. Now what I told you in terms of pKa was that at equilibrium, 99.99, 16 other nines beyond that percent is going to be in the enolate form, and basically 0 is going to be in the starting material. What that tells you is the position of this starting material relative to the position of the enolates is going to get way higher in energy. So let's just put it way up here. Starting out with something that's really reactive, now you're going downhill. Okay, so I'm going to erase the red energy diagram because we're going downhill. The pathway, though, to those two enolates downhill is going to be basically, is going to have the same features as it did up here. That is, the transition state leading to the more stable enolate, the transition state where the more sterically hindered proton gets removed is still going to be higher in energy. So this is our purple transition state, and it's higher in energy because of steric hindrance. Whoops. And then the orange transition state we'll simply draw as being the lower in energy pathway. And that transition state's lower in energy because of less steric hindrance. We've still got, and so the difference in energy between these two lines is essentially a kinetic issue. And it tells you that the orange enolate forms fastest. The difference in energy between these two lines is essentially a thermodynamic issue. The more substituted enolate is still more stable, but under irreversible conditions, thermodynamic issues don't matter. The only thing that matters is who's fastest to form, because once you go over either of these hills, you're done. There's no going back. And so, the hill that's fastest to go over is the one that will happen most frequently. Okay? We will sometimes use the term kinetic enolate for the enolate that is fastest to form. Enolate chemistry is an example of a situation where the kinetic enolate, the one that forms fastest, is almost always not the thermodynamic enolate, that is, the enolate that's more stable. It doesn't have to be that way, and you should not take from this section of the class the idea that the kinetic product is always different from the thermodynamic product. Those are two separate issues. The kinetic product is the one that forms fastest. The thermodynamic product is the one that is most stable. Sometimes those two will coincide. It just so happens with ketone enolate chemistry, they don't. Yeah?
Explain again why the original reactants are higher in energy.
It all has to do with the reactivity of this base.
Okay.
Come back up here and remember that if we use OH minus as a base, we're competing between these two acids, water pK16 with, the ketone, versus here, a lithium disopropyl amine pKa 40 versus the ketone. Yep. All right. Anything you want to ask about that? Yes.
So if I understand correctly, with ketones to enolates, we're always talking about most substituted being the slower forming.
With ketones going to enolates, the more substituted one, because of sterics, will be slower to form, yeah. Yep. Now, one other thing I guess I should mention about irreversible conditions. We often worry about well, let's just say this. If you use water as your base, you go to reversible conditions, right? So naturally, if you're going to use LDA as your base, you need to have no water present, right? If you did, the first thing that happened would be LDA would remove a proton from water, and then you'd be back here. So it'd be a terrible waste of time and money. So an important aspect of LDA and irreversible enolate conditions is you want it to be anhydrous. That means no water. We don't typically talk about solvent, but you're going to want to use a solvent with no acidic protons whose pKa's are less than 40. So typical solvents for LDA involve things like diethyl ether or THF. These are polar but aprotic solvents. That's not really anything to memorize. It's just guidance for when you're doing problems in the text and you see things like THF or ET2O. Those are just all solvents that are appropriate for using LDA. Another practical aspect is that these reactions are almost always carried out at low temperature. The low temperature helps prevent what's called enolate exchange. So I told you that the reaction's irreversible, meaning as soon as LDA removes a proton, you're done. And that's true as far as LDA is concerned. The enolate is never getting the proton back from LDA. However, if you're not careful, and if the reaction is slow, it is possible for one enolate to steal a proton from another ketone, and then you're right back in the equilibrating issue, right? And equilibrating to form the more substituted, more stable enolate. So you want to avoid enolate exchange. And this is just a practical issue. It's not, we're going to assume that for your purpose, you don't have to, like, every time you propose a reaction, write down all of these conditions. We're just going to assume that that's the case. But I want you to be able to understand why your text puts in some details that may otherwise seem confusing. To avoid enolate exchange, you're going to use low temperature. And you're going to see a particular number here, minus 78 degrees Celsius. Just like on the labels of food, where 0 grams trans fat does not really mean 0 grams, but means less than 500 milligrams, minus 78 C doesn't necessarily mean exactly minus 78 C. At certain atmospheric pressures, this is the temperature of dry ice, that is solid CO2, in acetone, both of which are very easy to get in the organic lab. Acetone's a very cheap solvent. Dry ice we've got tons of. So if you want to cool a reaction to low temperature, you take a container of acetone, you dump dry ice into it until it gets really cold, then you stick your flask in that bath of acetone and you stir the flask, and eventually what's in the flask gets down to that temperature, and then you add the LDA, and then you're good to go. So if you see minus 78 C and THF, all of that is just code for irreversible enolate formation, which you're going to assume we're using anytime we use LDA. All right. Anything you want to ask about that? Okay, we're going to talk a little bit more about reactions of enolates, but I want to before we do that, I want to just take you on a brief tour through the kinds of alpha protons that we will be removing in order to generate enolates. We'll do that. Let's take a few minutes now for break, and we'll start back up at 9. So I told you I wanted to talk about alpha protons, just so you can get a sense for alpha proton acidity, because some enolates are going to be easier to form than others. Fortunately, the trends in pKa's of alpha protons are going to track very well with what you already know about carbonyl chemistry reactivity. So, if I were to write a list of carbonyl compounds in order of increasing reactivity, I would start with an amide. We've said before that the reactivity of carbonyls really has to do with the fact that the carbonyl carbon is electron poor, and you can draw a resonance structure with a positive charge on the carbonyl carbon. But when it comes to the amide, you've got this neighboring heteroatom with lone pairs on it that can donate electron density into the carbonyl carbon via resonance. And nitrogen is a good electron donor. It's better of an electron donor than oxygen because nitrogen's less electronegative than oxygen. So it turns out that the carbonyl carbon of an amide is relatively electron rich, and so the amide is less reactive in terms of being a carbonyl compound. Accordingly, the pKa of the alpha proton is also less reactive. pKa is 30 for the amide. And some of this gets into why, well, so let's talk about why that might be and compare pKa for the ketone was 20, pKa for the alpha proton for the amide is 30. Why is it so much less acidic? Nitrogen's more electronegative, but yeah. What makes the alpha proton acidic in the first place is the fact that you can draw a resonance structure for the carbonyl compound that looks like this. And it's almost as though from this resonance structure you can draw almost an E1 type reaction mechanism where a base removes a proton and then you create a new pi bond. That ought to look a heck of a lot like an E1 type reaction. To the extent that you minimize, if you make the carbonyl carbon less electron poor, then that elimination reaction or deprotonation reaction gets less favorable. The alpha proton gets less acidic. The thing that made the alpha proton acidic in the first place was the fact that if you removed that proton, you could get to a resonance stabilized resonance stabilized anion, which we called the enolate. And we could have drawn a resonance structure for the enolate. We didn't draw this one, but we could have. That looks like that. The only thing that made that alpha proton acidic in the first place is because the carbonyl carbon was electron poor. There's more to it than that. There's a hyperconjugation explanation that we could talk about, but it won't necessarily add to our understanding, so I'm gonna skip over it. But in general, if you have electron donating groups attached to the carbonyl carbon, that's going to make the alpha proton less acidic. All right? So, let's see. All of this is just explanation. We're going to put the ketone. I don't know what we're going to do with that.
Right.
Yes.
But another way to say that is to make the carbon electron rich.
Right. If you make the, yes, less electron poor would be more electron rich. Good. Yeah.
Just double check.
Yep. If you make the carbonyl carbon more electron rich, then the alpha proton is going to be correspondingly less acidic. Okay, so what do you predict if we replace the nitrogen with an oxygen? What do you predict for an ester? Is that pKa for the alpha proton going to be higher or lower than for the amide? Oxygen, let's just draw the oxygen real briefly here. Here is the ester, here is the alpha proton. You can also draw a resonance structure with the carbonyl carbon being positively charged, the oxygen here, donating electron density into that positive charge to give you this resonance structure as well. Differences between ester and amide. Yeah.
The O is more electronegative, so it's probably not going to donate as much.
Right. Oxygen is more electronegative. That's my symbol for electronegative. Electronegative than nitrogen. Therefore, oxygen is a poorer electron donor. Therefore, the ester carbonyl is less electron rich than the amide. Therefore, the ester alpha proton is more acidic, less electron rich, or alternatively more electron poor. Oxygen is a poorer electron donor. And indeed, the pKa for the ester is about 5 orders of magnitude lower. Okay? We've already said for the ketone that the pKa is 20. And presumably by that we infer that even though CH3 is an inductive donor of electron density, it is not as good a donor as in the ester or the amide. I'm not going to continue to draw these resonance structures because I think you get the idea. Perhaps I just said I wasn't going to do it, now I'll do it. It's the parable of the two sons. Go labor in my vineyard. I go, sir. And then he went not. Okay. Right. This is an sp2 carbon. sp2 carbons are more electronegative than sp3 carbons. So you can donate electron density via a dipole into that positively charged carbon, but that is called inductive electron donation, and that's not as big of an effect as is resonance donation. And therefore the ketone is more reactive than the ester or the amide, as we've already learned, but the alpha proton is correspondingly more acidic. Okay? So make a prediction. If I put the aldehyde on this list, where's it going to go? Look at the aldehyde structure. Now, instead of having a methyl group, you just have a hydrogen. The hydrogen, by virtue of being small, doesn't come with a lot of electrons. There's not a lot to donate. So the pKa of the aldehyde is 17. The carbonyl carbon doesn't have as many sp3 hybridized carbons attached to it in the aldehyde versus the ketone. So the aldehyde carbonyl carbon is more electron poor than the ketone, and therefore the alpha proton is correspondingly more acidic. All right. Yes?
Explain one more time the difference between an inductive donor and the oxygen nitrogen. It says there are two tiers.
Right. So the major effect with the ester and the amide is called a resonance electron donating effect. That literally means the lone pairs on the nitrogen are conjugated to the carbonyl, and that lowers the, that makes the carbonyl more electron rich. An inductive effect is the reverse, an inductive donation effect is the reverse of electronegativity. So just as, or it's the flip side of the electronegativity coin, right? You're probably comfortable saying that because fluoro is more electronegative than carbon, the fluorine should be electron rich, the carbon should be electron poor. And we framed that in terms of fluorine is pulling electron density away from the carbon, right? And we viewed that mostly as well because fluorine is more electronegative than carbon. But it's also true that carbon is more willing to let go of electrons than is fluorine. So we've got an analogous situation here. The sp2 hybridized carbon of the carbonyl is more electronegative than the sp3 carbon for reasons we discussed in 351. And that means that the sp2 carbon should be able to pull electrons away from CH3 just through the sigma bonds. So naturally, the more CH3 bonds you have, the more bonds to alkyl groups you have, the more that carbon's going to be able to take electrons from them. So an inductive effect is really based on electronegativity differences between two atoms. Resonance effect is based on having lone pairs, well, in terms of how we're talking about it, having lone pairs adjacent to things that can donate into or be conjugated to the carbonyl carbon. All right, what else? So we can cheat actually and make some super acidic carbonyl type compounds. The aldehyde already is acidic enough that in water, or rather if you use sodium hydroxide as a base, about 10% of your aldehyde should be present in the enolate form, because you'd be comparing a pKa of 17 for the aldehyde to a pKa of about 16 for water, the conjugate acid of your base. So let me just show you a couple other ketones or carbonyl derivatives that have especially acidic pKa's. If you make a dicarbonyl compound, what I'm showing you here is called a beta diester. It is so called because if you define this as a carbonyl carbon and this is the alpha carbon, on the beta carbon relative to the blue carbonyl carbon, you have another carbonyl group. So in other words, the alpha protons are alpha to two different carbonyls, blue carbonyl and orange carbonyl, beta diester. And you can mix and match carbonyl compounds here. You could have a beta ketoester where one of these would be a ketone instead of an ester, and those kinds of compounds are known. You could have a beta diketone as well. So here's a beta ketoester, and here is a beta diketone. The alpha protons here are alpha to two carbonyl groups, and so they are correspondingly more acidic. The pKa of this proton on the beta diester is 13. That's more acidic than water. The proton on the beta ketoester has a pKa of 11, and on the beta diketone, it's ridiculously low, around 9. The reason for The reason the pKs are ranked like this, notice that it tracks with what we already know for alpha proton acidity. Esters, protons alpha to esters are more acidic than protons, are less acidic rather than protons that are alpha to ketones. So as we introduce or replace an ester from this beta diester, replace one of them with a ketone, we get more acidic. We replace the other one with a ketone, we get correspondingly more acidic. So it sort of tracks in that way. The reason the pKa's are so much lower than for the individual carbonyl compounds are, let's just draw the conjugate base of, say, the beta diester. And you can realize if you do that, that now instead of having only one enolate resonance structure where the negative charge is delocalized on an oxygen, now you have an option for a second resonance structure in which the negative charge is delocalized on the other oxygen. So more places to delocalize the negative charge in the conjugate base, correspondingly more acidic. So we're going to see later on, there will be times where we want to use hydroxide as a base, but we want to do quantitative 100% enolate formation. You can do that with these beta dicarbonyl compounds because hydroxide is a good enough base to completely 100% remove the proton. All right. So that's your whirlwind tour through carbonyl compound acidity. My son Dallin is texting me saying, I have to keep my phone here because I can't tell what time it is because it's always 9:41 on Tuesday, January 9th. But now I'm getting texts from my 15-year-old who wants to go skiing tomorrow.
Oh yeah, at Sundance.
Are they opening tomorrow?
Yeah, just the back mountain.
Just the back mountain? Is it? Okay.
Mother's Day. That's what they said at least.
For Mother's Day, okay.
For money?
For money, yeah, that's.
Yeah.
Money's Day.
For Money's Day.
I
I would open it for money.
Yeah, that's interesting. I didn't. Okay, I imagine it's going to be pretty slushy and pretty rocky. Like
Sweet.
it's going to be sweet. Okay. Well, I'm still in physical therapy for an injury I sustained while at Sundance. Did I tell you guys about that? No, it's not a great story. It's a terrible story.
Did it treat you?
No, it's not even funny. It's just old guy. My son Adam, who's 11, wanted like, Dad, let's go down to the terrain park. Like, okay, and we're watching these cool guys like go off jumps, and Adam's like, I want to go off a jump. Okay, and you know, if you control your speed, you just sort of go over the hill, and then you can feel like you did something cool, even though you didn't. I didn't control my speed very well, and I didn't land the jump, and I fell down on my shoulder, and it's like a partial. Anyway, it's not even bad enough that they need to do radiology, but it's bad enough that as a 40-year-old man, if I go to put my arm around my wife, I'm like, ow! And so, yeah, I'm doing a bunch of physical therapy to get me back to whatever. It's embarrassing when you get old. Don't get old. But also don't do stupid things on Back Mountain tomorrow, okay? Okay, got it? All right. Oh, sorry, that was an unnecessary aside. Let's see, let's talk about enolate chemistry now and show you some examples of what we can do. Reaction number one is called enolate alkylation. That means we're going to be doing substitution reactions, basically SN2 reactions with enolates as nucleophiles. Your concerns here are going to be related to similar, should be related to concerns you've had before for SN2 reactions. That is, you're going to be worried about the substitution of the alkyl halide. Let's see, using enolates as nucleophiles and alkyl halides as electrophiles. So just to set things up, remember that for the SN2 reaction, primary alkyl halides are fast, secondary alkyl halides are slower, and tertiary alkyl halides are no good. Also remember the potential under, especially when you are using reaction conditions where your nucleophile is a base or could be a base, you have the potential for competing E2 reactions, which are for primary alkyl halides slow, and so SN2 wins. But for secondary alkyl halides, they're competitive with SN2. So in general, remember, enolate formation involves a strong base. And so in general, for enolate alkylation, we're going to want to avoid times and situations where we can have SN2 and E2 compete with each other. So in general, we're going to stick to the primary alkyl halides as electrophiles. And should you decide you want to attempt something like enolate alkylation with a secondary alkyl halide someday, you will know that it probably isn't going to work, and you'll know if it doesn't work, you'll know why. So let's talk about sort of the simplest case for enolate alkylation, and that's using irreversible enolate formation. That is, we're going to use LDA. We're going to lead with what works, I think. All right, so here is our starting material, ketone. This is a classic example in enolate chemistry because it has a 6-membered ring, which organic chemists like, and it's got 2 different kinds of alpha protons. If we use, what we're going to do for quantitative enolate formation is we're going to use LDA, and we're going to do this again at minus 78C and THF as our solvent to prevent equilibrating conditions and to prevent enolate exchange. That's going to generate exclusively, or hopefully in some major percent yield, oops, wrong color. LDA should remove the less substituted alpha proton fastest. So that should get us to this less substituted enolate, which I can draw in either of these 2 resonance structures. Then, once I've quantitatively formed this enolate in 100% yield, and only then do I do the second step, which is I'm going to add my alkyl halide. So let's just choose this primary alkyl halide. The mechanism is SN2. Whoops. Of course, since we're using a primary alkyl halide, there's no stereo center on that carbon that has the bromo group. We make a new carbon-carbon bond between the carbon that had the leaving group in our alkyl halide, the blue carbon, and then the orange alpha carbon. I'm going to draw that new bond in red, and that's the product for enolate alkylation.
Your mental bridge should be on the opposite side.
Huh? Oh, thanks. Thanks for keeping me honest. Yeah, there was no secret carbocation rearrangement. Are we recording? Yes, we are still recording. Good. All right. So that is a clean way to make the product where you put the alkyl group on the less substituted carbon. Now let's just think about another option. What if we wanted to get as a product the one I was trying poorly to draw? What if we wanted to get this one as the product?
We use equilibrating and then distill out.
So yeah, let's use equilibrating enolate conditions. That means that we start with the same starting material. Again, we note the presence of the less substituted alpha proton and the more substituted alpha proton. And in this case, let's use a base. Your choice of base here doesn't, for equilibrating, you just want something that's about the same reactivity as OH minus. A common base that your text uses is sodium ethoxide, which they abbreviate as NaOET. Hydroxide would be okay here. I'm going to just use something that your text uses. When you use sodium ethoxide, some of this may have to do with solubility. Sodium ethoxide is soluble in ethanol as a solvent, and that's an organic solvent in which a lot of organic starting materials are soluble. So this is probably simply a solubility choice in terms of what base you use rather than any difference in reactivity. But if you use ethoxide as your base, you are in an equilibrating situation because the conjugate acid of ethoxide is just ethanol, and its pKa is about 16, which tells you that 99.99% of your material is starting ketone with 0.01% as enolate. And then once you've done that, you're not isolating this enolate. You can't really, there's no really good way to isolate the enolate. That's kind of fun. Instead, you just start adding your alkyl halide to the solution and you hope for the best. Now, if you are lucky, your enolate attacks the, whoops, where do we want to go? Your enolate does SN2 with the alkyl halide to make the new bond that's shown there. Some of you should be looking at that and feeling uncomfortable about some potential side reactions. Got anything? On which oxygen to make the ether? Okay, so that's interesting. Yeah, so that might be a problem for both of these. The question that's being asked is, do you ever do SN2 with the enolate and alkyl halide such that the new bond is with the carbonyl oxygen? In other words, do you ever get up here, it would be this product. This is called an enol ether. And the product down here that you're proposing is this enol ether. The answer is generally not. And I can tell you why, but maybe I'll hold off on that for just a second. So, yeah, there's a reason why this doesn't happen. You're right to be worried about it. There's something else. if I try this and I've got 99% ketone and 0.01% enolate, how much of ethoxide do I have? Okay. And when you were in 351, what would you have drawn as a potential reasonable product if ethoxide and the alkyl halide ever saw each other? Undesired SN2 Williamson ether synthesis product. Okay, I call that the Williamson ether synthesis because that's actually a reaction you're going to do in 352. Sometime I'll tell you the story of how I ruined and then saved my Williamson ether synthesis reaction in 353. But in any case, yeah, this is something your text doesn't necessarily mention or worry about it, but I'm worried about it because you can't make the enolate 100% using this method, so there's still going to be base around, and that base also happens to be a good nucleophile. There are probably practical ways you can sidestep this issue, but this is a concern. We're going to let you continue to pretend like we live in a world where this reaction works, but if you actually go and try it, you should be worried about it. All right, Hunter, did you have a question?
No.
Okay. 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 So the irreversible enolate formation to get you the the alkyl group on the less substituted carbon works pretty well. You can pretend like and assume that the equilibrating enolate formation works okay to give you the alkyl group on the more substituted carbon. You can pretend like we live in a world where that works all the time, but if you have some concerns about the method, then that's good. And we're actually going to introduce some alternative methods for doing enolate alkylation, and the rationale for those alternative methods really is it helps us avoid this competing background ether synthesis. All right. Questions? I guess maybe it's worth backing up just a little bit and trying to give you some more background on why we don't form those enol ethers. And it has to do with MO theory, so that's already, your eyes can glaze over and that's all right. I want to show you what the results are for qualitatively for some MO theory calculations on an enolate. So I'm going to just simplify the enolate if that's okay. It turns out that the enolate is not so very different from an allyl anion. And if you recall, those of you that took 351 from me, we talked about the molecular orbitals of the allyl anion. In particular, the highest occupied energy orbital is one in which there's a node in the plane of the page, and there's, you're using color to represent sign of the wave function. You have atoms 1, 2, and 3. And there is orbital on atoms 1 and 3, but never on 2. Is that sounding sort of vaguely familiar? We'll take the top view over here. Pi 2 is the highest energy one, atoms 1, 2, and 3. Pi 1 is an orbital in which that is delocalized evenly across all 3 atoms. Pi 2, we've said, looks like this, and then pi 3, the top view is sort of this one where the wave function sign alternates in between atoms. You've got a node here in between atoms 1 and 2, in between 2 and 3. For the pi 2 orbital, you have a node that actually coincides with the position of atom 1. When you introduce oxygen instead of carbon, that changes. That will still have the same overall features of our pi system orbitals, but the fact that oxygen's lower in energy, more electronegative than carbon, changes the relative shapes of the orbitals. Notice that for the allyl anion pi system, the size of the orbital is the same on atoms 1 and 3 in all of these orbitals. It has to be because of symmetry. When you change one to oxygen, it doesn't have to be that way. I guess since we're rushing through this, I'll just point out for the allyl anion that the highest energy electrons, the ones associated with the lone pair, is on carbons 1 and 3, but never on carbon 2. Similarly, the electrons that are sort of associated with the pi bond, by resonance, you could see those are evenly delocalized between carbons 1, 2, and 3. In other words, they're spread out over all 3 of the carbons. So the lower energy electrons represent the 2 electrons that are in the pi bond that can be spread between 2 and 3 and between 1 and 2. The higher energy electrons are on carbons 1 and 3, but never on 2. Is okay with that? All right, so when we change and use oxygen, what that does is it distorts the shape of the orbitals a little bit. Oxygen's more electronegative than carbon, and what this means is that the lowest energy orbital, the pi 1 orbital, is going to, we'll say oxygen is 1, and then you got carbons 2 and 3. Are we having a day of Pentecost experience here with rushing sounds of wind? I think they're working on the air system, so okay. We could go into the lecture prep and blow some stuff up, and then we could have cloven tongues of fire as well. That would be kind of fun. All right, yeah. So you can at the end of semester say that that the day of Pentecost jokes were a bit much, and that's fine. So oxygen being more electronegative than carbon, the lowest energy electrons are going to be the ones that are pulled more towards oxygen. So the amount of orbital on oxygen is going to be bigger in pi 1. And in pi 2, the amount of orbital on oxygen is going to be correspondingly less. So MO theory tells you that the pi bond electrons are pulled more towards oxygen. Whereas the highest occupied occupied MO electrons are pulled more towards the alpha carbon. So it turns out the enolate is literally more nucleophilic on carbon than it is on oxygen, and that's why you don't get very often the enol ether. All right, that's kind of an aside. Your text doesn't talk about it. I promise not to ask you about that on the exam, but sometimes you want to know stuff. If you don't, go ahead and put that in the filing cabinet in your brain that you'll never open again. And then pray that that's the one that starts on fire when you, when you have your testing center SpongeBob moment. Okay. Enolate alkylation. We've talked about regioselectivity, talked about how to do this by either making the more substituted thermodynamic enolate under reversible conditions, but we're worried about potential side reactions, or irreversible conditions where we get them less substituted enolate. So now we're going to talk about some workarounds that allow us to avoid, number one, using expensive LDA as a reagent, but also avoid using this these weird equilibrating conditions. Ideally, we'd like to have a world where we could make the more thermodynamic enolate and make the most stable enolate and make it quantitatively 100%. Then kinetics and thermodynamics would be reinforcing each other. So the strategy is to use, as with all strategies, it doesn't solve all of the problems, but it works for an interesting subset of situations. And it involves the beta dicarbonyl compounds. Now, your text will call this section the two things. It will call this the malonic ester synthesis, and it's going to group that with the acetoacetic ester synthesis. And I frankly don't like those titles because in those two approaches, these two workarounds, malonic ester and acetoacetic ester are the starting materials, not the products. So perhaps more appropriate would be the synthesis that begins with the malonic ester or the synthesis that begins with the acetoacetic ester. Nevertheless, that's not what your text has chosen to do. Malonic ester is a beta diester that looks like this. I've already drawn it for you when we were talking about pKa's of alpha protons. Remember that pKa was like 13. Acetoacetic ester is this one. You will not be synthesizing these two molecules, at least not yet. In a future chapter, you will learn how to do it. Rather, you will be doing synthesis with these two molecules. So perhaps we could call this section alpha alkylation of enolates, starting with beta dicarbonyl compounds. That's a mouthful, and so I can see why your text has chosen to call this the malonic ester synthesis or the acetoacetic ester synthesis. Okay, let's start with acetoacetic ester. And let me just show you what we can do with this starting material. As I said, the pKa of this proton is 11. What that means is I can use sodium ethoxide as a base in my first step. I am choosing sodium ethoxide deliberately because my ester is an ethyl ester, and I have I'm worried about the potential side reaction whereby this negatively charged base attacks the carbonyl carbon to give a tetrahedral intermediate. Now, I'm not going to draw the product that happens from that, but just imagine it. Actually, sorry, I am going to draw the product that happens from that, and you can imagine it. What's going to happen at that stage? Going to kick something off. Does it matter which one you kicked off?
No.
And can you ever tell that the attack even happened? No, and that's why we choose ethoxide. We match the ester, we match the identity of the R group on the ester with the base that we use. Some of you are saying now, thinking, well, what if there's some big elaborate thing over here? Do we choose that base? No, we wouldn't bother with this type of reaction if we had a big elaborate R group on this ester. So in general, the examples in your text are almost always ethyl esters. You're going to use almost always sodium ethoxide, such that the attack of the carbonyl compound, though it does happen and it's happening in the background, you can't tell that it happened, it's inconsequential. Now, ethoxide is a strong enough base to quantitatively remove the proton from the alpha carbon of acetoacetic ester. To generate this enolate, I'm drawing this resonance structure, though you should be able to see in your mind how that negative charge is delocalized on those three positions. You can tell that this reaction is 100% quantitative simply by writing the conjugate acid of your starting base, ethoxide, whose pKa is 16, pKa of 11, strongest acid loses its proton, no problem, right? So 100% yield, irreversible. Incidentally, this is also, so this is the kinetic enolate, it is also the thermodynamic enolate. Why did we not remove this proton whose pKa would be around 20? Because it's a billion times less acidic, that's why. Right? So the beauty of the beta dicarbonyl compound is that the enolate that is fastest to form is also the most stable enolate. Kinetic and thermodynamic enolates line up here. And so that's the real advantage of what we're doing. Then in a second step, you can introduce your alkyl halide. And then you do the SN2 reaction. And that gives you this product. Okay? Now let's talk about what you can do with this product. That was alpha alkylation, right? We have an alpha carbon. We have now installed an alkyl group on it. Yeah?
Will it attack from both sides?
Yes, if you make a stereocenter, you're going to get from above or below. Now, the other advantage of this method, aside from aligning the kinetic and thermodynamic issues, the other big advantage here is that the product we form, we can use to do other things. So, for example, I'll show you a couple of different things you can do with this product. We could, if we wanted to, introduce another equivalent of base to generate, and again, this proton here is still alpha to 2 carbonyl groups, so its pKa should still be 11. We still have hope here of forming this enolate in an irreversible fashion, 100%. And then we could do a second round of alkylation, and perhaps this time we want to put something else on there. We can install using this method, we can install not just one, but 2 different alkyl groups. 1, 2, 3, 4, 5. 1, 2, 3, 4. Something like that. We can install 2 alkyl groups to get this alpha-alpha dialkylated carbonyl compound where the 2 alpha substituents are different. Notice that we could not have done that via the previous approach. Using lithium diisopropyl amide, we can selectively put an alkyl group here on the less substituted carbon. We had an approach previously for doing that using equilibrating conditions. This molecule is also alpha-alpha disubstituted or dialkylated, but we were worried about this potential side reaction. Now, using our new method, we can install 2 alkyl groups on the same alpha carbon in subsequent steps, and we do it without any competing kinetic or thermodynamic issues. All right? That's not all. There's more, because both of these products, we can go on to do a simple workup that actually gets rid of the ester group entirely. And we're going to talk about that next time. That's called decarboxylation. So our schedule has 2 days on Chapter 17. So we're pretty far through Chapter 17. We'll finish it up next time. I wish you lots of luck on the exam. Make sure you give yourself plenty of time to take it before the testing center closes. Good luck. This is the way.